Okay, we are recording. So today we are going to do more exercises on the public key cryptography, especially on the RSA algorithm. Okay, so let's do exercise 8. So it's ASCII is a standard way to represent character as number. For example, a space is represented by 32, a comma by 44, and a period by 46. The capital letter are also 2-digit integer and are given in the following table. You have the following public key. E is equal to 17 and N is equal to 629, where E is the public exponent and N is the modulus. The following message, where each ciphertext represents a character, was encrypted with this key. You are asked to decrypt the message. Okay, so we have a message that was encrypted with this key, this public key. And we are asked to decrypt the message. So the way to proceed, of course, is we need the private key, because what was encrypted with the public key must be decrypted with the private key. So for that, we need to find the private key. And since the modulus is a small number, there is no problem to find the private key. So the modulus n is 629. So n is 629. So we are going to ask our virtual machine with the command factor. We are going to factorize 629. And it has to be the product of two prime numbers. And those prime numbers are 37 and 17. So it's 17 times 37. So we can take, for example, it's a possibility, P equal 17 or P equal 37. Once you choose P, the other one will be Q. But it doesn't matter, because what we need is the totient, and the totient is P minus 1 times Q minus 1. So at the end, it will be the same value. Whatever value I take for P, if I take 17 or if I take 37. So this will be 16 times 36. And 16 times 36, we are going to ask our virtual machine to do that. So echo 16 times 36. It's 576. So it's 576. So we know that to find the private key, we need to resolve this equation. The public exponent times the private exponent is equal to 1 modulus the totient. So we have E, which is the public exponent. So the public exponent is 17. So we will have 17 times D must be congruent to 1 modulus 576. So we are going to resolve that, as we already learned how to resolve it. So we are going to express 576 in function of 17. So 576 is 17 times something. So this something, let's ask our virtual machine to compute it. I'm going to put here 576 divided by 17. It will be 33. And the modulus is 50. So it will be times 33 plus 15. Times 33 plus 15. So I don't have 1 here, so I need to keep going. And I need to express 17 in function of 15. So 17 is 15 times 1 plus 2. So I don't have 1. I still have to keep going. So here I'm going to express 15 in function of 2. So 15 is 2 times 7 plus 1. Bingo, I have the 1. I can go back. So I'm going to take advantage of this first line and say that 1 is 15 minus 2 times 7. Then here I'm going to extract the 2 and replace with the 2 here. So it will be 15 minus 17 minus 15 times 7. And I'm going to express all in function of 15 and 17. So 15 minus 17 times 7 plus 15 times 7. So this gives me 15 times 8 minus 17 times 7. Just in case, to be sure I didn't make any mistake, let me verify that this is 1. So let's see, we need to do 15 times 8 minus 17 times 7, and it's 1, as you can see. So I'm going well. Okay, so now we are going to take advantage of this line and replace the 15 by 576 minus 17 times 33. So the 15 is 576 minus 17 times 33, all times 8 minus 17 times 7. And now I'm going to express all in function of 17 and 576. So this will be 576 times 8 minus 17 times 33 times 8. I need 33 times 8. So let's see that. 33 times 8 is 264. So here 264 minus 17 times 7. So it will be 576 times 8 minus 17 times 264 plus 7 will be 271, no? Okay, let's verify that to be sure that we didn't make any mistake, that the result here is 1. So I'm going to do 576 times 8 minus 17 times 271. And it's giving me 1, so I didn't make any mistake. So at the end, what I want the inverse of 17 modulus 576. So the inverse of 17, since I have modulus 576, this will disappear. So the inverse of 17 is 271. So the inverse of 17 is, sorry, negative 271, no? And negative 271 modulus 576 will be 576 minus 271. So I'm going to do that. 576 minus 271, and it's giving me 305. So I'm going to verify it to be sure that I didn't make any mistake before we proceed. So I'm going to say, please verify that 17 times 305 modulus 576 must be 1. Okay, it is 1. So perfect. I did find the inverse of 17. So what can I say? We have the private key. Let me write again the public key. So the public key that was given to us is 17, and the modulus was 629. 629. And the private key, which is a pair of integer, is the inverse of 17 is 305, and the modulus is 629. So I could find the private key without problem because the modulus is a smaller integer. So now I need to invert this to know what was written here, what was transmitted. So to do so, I'm going to use my Python calculator. I'm going to use Python. Let's see if I can accommodate that like that. Okay. So Python 3. Okay, I'm going to create a decrypt. Decrypt is Y, no? A decrypt function that will receive C, which is the ciphertext. So define this function as return. So what should I return? To the power of D. And D is 305, no? Yeah, 305. So C to the power of 305 modulus N. And N was the modulus 629. 629. Okay, I have my decrypt function done. So I can decrypt, for example, 247. It will be an integer that represents an ASCII code. So this 77 is the ASCII code of a letter. I can check an ASCII code in some places, or I can just transform that into a character, and it's giving me an M. So this message starts with an M. Then we have 327A, so it starts with MA, 322T, then we have 463. 463 will be H. So it starts with math, as you can see, no? If I can handle that, still handle that. Okay, so it starts with math. Then we have a 15. 15 is the right space. So there is a word that says math on the right space. Then we have 73. 73 is I. Then we have a 440. We have a S. Then we have a 15. The 15 will be a space again. Okay, because we already did 15 and it's a space. So math space is space, and we still need to find 3 letters. 342 is a F. 323 is a U. And we are, so math is, I can imagine my math is fun. Let's see if we can have the last one. So the last one is 435. Yeah, math is fun. As you can see, math space is space fun was the message transmitted. Okay, so this is a way to do it. Another way, there is another way. We don't need to compute the private key. Do you have any idea of what we can do if we don't compute the private key? We can generate a table of the encryption of all possible plain text. So how many possible plain text we have? 629. They go from the integer 0 to the integer 628, both inclusive. So I can do the table, and with the table I can go back. So let's see this possibility. It's a long table, so of course I'm going to use Python to help me with that. Let me go to the desktop and we are going to edit a file. So this file, let's call it full table, because it's going to give us the full table.py. So the hash band, the path where is Python, it is in user bin Python, and of course we are going to use Python 3. Okay, we are going to import first sys, because we are going to put command line, command argument. So if the length of sys.argv is not 3, we are going to put the way that the person should use it. So the way that the person should use it is, let's put here usage. We are telling the person this is the way that you have to use it. The file where we want to send that is sys.standarderror. Okay. Then we are going to specify the usage. So the command name, the first argument should be what? The public exponent, no? The public exponent. And the second argument should be the modulus. Percent. And here, instead of %s, we want sys.argv sub 0. Okay, and then I'm going to exit, showing that there were a problem. And then here, I'm going to exit, showing that everything was okay. So let me verify that this works fine for now. So it is in the desktop. Going to give me the right of execution over the file full table.py. And I'm going to execute full table.py. So look at it. Tell me, okay, you forgot to specify the public exponent and the modulus. So the way I should use it is, for example, in this case, the public exponent is 17 and the modulus is 629. And I want the whole table. So here, it didn't show any message because it exits here, no? Okay, so now we can get the public exponent. Public exponent will be what? It will be stored in sys.argv sub 1, isn't it? But this is a string, so I need to convert it to an integer first. Then I need the modulus. Modulus will be where? In sys.argv sub 2, isn't it? So also it's a string. I need to convert it to an integer. So I convert it to an integer. Okay, we have both. So what should we do? We need to show the plain text and the ciphertext for all the possible value. So let's do a for loop. For I in range of what? So from 0 inclusive to modulus minus 1 inclusive. So I'm just going to put here modulus. It will go from 0 inclusive to modulus minus 1 inclusive. So what should I do? Okay, look what I want to do. I want to show, for example, let's say We are going to put, yeah, let's pay M. M of, for example, something, I don't remember, 247 was 66, if I remember. M of 66 will be 247. If you encrypt 66, 66 was, this is math. So 66 was, no, it's 777. So the first one was 77, no? So I want math, sorry, if you encrypt 77, it will give you this is, if you encrypt A, it will give you 337. I want that. And since it will be very long, I'm going to put 4 in a line. So to do so, I'm going to say if I modulus 4 is 0, or is different of 0, better. If it's different of 0, I'm going to print some space, which are separator. I'm going to stay in the same line. Then I'm going to print the value. So I'm going to print M over 4 characters. I'm going to print a decimal number, an integer which is in decimal, and over 4 characters, I'm going to print another decimal number. So this first decimal number, the first one that go inside the parentheses of the M, will be I. And what will be the second one? The second one will be encrypt I. So how do I encrypt I? I do I to the power of the public exponent modulus the modulus. And the modulus is in modulus. Okay, and after showing 4 value, I need to go to the next line. So I'm going to say if I modulus 4 is equal to 3, go to the next line. So I'm going to do a print that will take me to the next line. Okay, I think I'm done. Maybe I do a last print at the end, because I might have, for example, some numbers that are not multiple of 4. So I ensure that I go to the next line. Okay, let's see. Let me run this. Okay, let's see if we did it well. So for example, you see we have 4 value. And of course, wow, it's long. Let me maybe put less here. Okay, for example, if you take the plain text 0, the ciphertext will be 0. The plain text 1, the ciphertext will be 1. The plain text 2, the ciphertext will be 240. So let's verify some. We know that this is math. So we know that M is 77. The plain text 77 is 247. Then the plain text 65 is 337. Then the plain text T, which is 84, must be 322. Then the plain text, let's do up to T. The plain text 84, a space, so it's 32. A space is 32. Okay, let's do that. Let's verify. For example, 77 should be 247. Where is 77? 75. Look at, if you take the plain text 77 and you encrypt it, it will be 247. Good. Let's verify that 65 will be 337. 65 is here. If you encrypt the plain text 65, it will give you 337. Good. If you encrypt 84, it should give you 322. So let's verify that. 84 is here. Okay, as you can see, it works. So as you can see, in this case, how do I work? For example, I have a 73, and I want to know the clear text, the plain text. What can I do? I look for 73 in the result. So I need 73 in the result. So let me grab some line that have space 73. Here it is. So 73, the ciphertext 73 corresponds to a plain text of 73. So here it will be a 73. On 73, if I look, it have to be, because it's is, it have to be an I. Here it is. This have to be a S, 440. So let me go back to my virtual machine and look for 440. So it might take me a long time. I can do that. Here it is. 440, the ciphertext is 83. So I know that here in the plain text, I will have 83. And 83, according to my table, is a S. So IS. Here we have a 15. So I need to find, let me ask it. Find the 15. So look at, we have a 15 here. It's not the one that we are looking. We are looking 15 as a result, not 15 as a plain text. So 15 as a ciphertext, it is there. And it gives me as a plain text 32. So here in the plain text we have 32. And we already know that 32 is a space. Look at, they say that at the beginning. 32, the space is represented by 32. So this is a space. And here, for example, we have 342. So let me search for 342. So 342, it is there. There will be a 232 also there. Which one of the two I have to take? The first one or the second one? So this one or the previous one? Let me see, where is the previous one? Or this one? So of course here, it means this is a ciphertext. And the plain text is 70. And here it means what? This is the plain text. And the ciphertext is 70. Which one I have to take? I am decrypting. If I am decrypting, I have a ciphertext. So I need to take this one. What I have is 342 as a ciphertext. So the plain text is 70. So here I say it's 70. And according to this table, where is 70? 70 is here. According to this table, this is a F of fun. So you see, I didn't compute the private key. I didn't compute it this time. So it's more like a brute force attack. I have all the possibilities. What happened that here, how many possibilities we have? 629. They go from possibility 0 to possibility 628. I have 629 possibilities. So it's something that I can manage. But if you have number with 1024 bits, this table will be a monster table. So you are not going to do it. It's too long. Just to generate the table, you might pass years. So you don't want to do it because you know the limitation of your computer. Okay? So two ways to solve the same problem. Okay, let's do exercise 10. Let's say, given the following data, so they give me a modulus, which is n, which is a product of two prime integer. So this one is a little bigger than the one that we have been managing so far. as you can see, no? They give me the public exponent, which is E, its value is 7, and they give me a ciphertext. So they say, given the following data, find the plain text. So hint, there are many websites where you can factorize prime number. You can factorize number you can do the prime factorization. Look, the factor of Linux cannot manage those big number. So let's try it. I do factor of this big number is too big. Oh no, it can manage it. Wow, surprise, good. Maybe because this machine is 64-bit, it's not a 32-bit. I tried in 32-bit, it was not. So look, this is P or Q as you want, and this is the other one. It's the product of two prime number. So here they say, in case you cannot manage it with factor, they say there are many websites where you can factorize number. For example, you can go to this website. Let's go to this website. Okay, so we are going to put our number here to see the prime decomposition. So let me copy the number. The number is this one. So where it is there. Prime factorization. So let's compare this result that I find this web page with the one that we have here. 298 blah, blah, 21 4453 blah, blah, 557. As you can see, we find the same thing for P and Q. Okay, so we do have web page when we have big number that they have their limit. Don't think that you are going to put any big number and they will be possible to factorize. Of course, they cannot, because that will say that RSE is not good anymore if we know how to factorize them. We cannot use RSE anymore. Okay, so they say that we have this ciphertext and we have to come back to the plain text. So what will be what do you think we should do here to find the plain text associated with this ciphertext? So we do have P and Q, no? So let me start Python. We do have P and Q. We know that P is equal to this first number, and Q is equal to this number, which is a prime number. Both of them are prime, of course, because the modulus is a product of two prime number, two big prime numbers. So those ones are much bigger than the one that we have been managing up to now. So what is, if I want to find the plain text, one method is, okay, let's try to find the private key. Can I find the private key with this number, or it will give me a hard time? I can try. But what is your idea? If you need to find, for example, we are not going to, I don't know if we write that by hand, it can be very long. So we need to compute first phi. And phi is what? P minus 1 time Q minus 1. So let's see how big is phi. Okay, this is phi. So we need to express phi, this big number, in function of 7. So I don't even want to write it, but is it short? I don't know. Let's see. Phi divided by, let's see, modulus 7. Modulus 7. It's 6. then we have to do 7 and 6. So the second line is easy. So no, it's not long. So you see it's not long. So let me do it. Okay, this big number phi, because we need to express phi. Let me start with over. So we have phi is equal 7 times a big number. Let me call it, let's call it A, plus 6. This is what we just saw, no? So now we can express 7 in function of 6. 7 is 6 times 1 plus 1. And we are done. We already have the 1. So 1 is 7 minus 6. And we have this 6 here. So 1 is 7 minus phi minus 7a, isn't it? So it's give me equals 7 minus phi plus 7a. So it's give me 7 times 1 plus a plus 1, minus phi. Okay, so since I'm looking for the inverse of 7 modulus phi, that will go. So what is the inverse of 7? The inverse of 7 will be a plus 1, isn't it? Modulus phi. So what is this inverse? Now it's easy for me to compute it. What is a? A is phi divided by 7. Okay? And since I have to do plus 1, so this number is the inverse of 7. Let's verify it. So I take this big number, d, let me call it d, the private exponent. So let's do d times phi modulus d times 7, sorry, modulus phi, and it have to be 1. Bingo, it's 1, as you can see. So we did find d. So we have everything. So what should I do? I have d, I have n, I have everything. So I can solve my problem. Let's see. What is n? N is there. Let me copy this big number and say n is equal to this big number. Okay, so they say they want you to, this is the ciphertext. They want you to find the plain text associated. So this is C. And how do I find the plain text? C to the power of d modulus n. Long. Let me control C it. So look at, we are going, this is C, this is D. So of course, doing that can take a long time. However, we do have a power function in Python that do the power modulus n. So we can do C to the power of D. If I do C to the power of D, it will take a long time. But I can do modulus n. This is the plain text. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 9, 8, 7, 6, 5, 4, 3, 2, 1. So you see, I was able to find the plain text. And this is the plain text of this exercise. Do you have any question? Did you understand? Okay, so as you can see, I play a lot with Python, no, to help me. Exercise 11. To encode a plain text message to an integer. So look at, first, you need to convert the text to an integer because we work with integer. With the public cryptography, the message is an integer. So you need to convert it to an integer. So they say to encode a plain text message to an integer m, we use the following algorithm. So look at, you receive a string, you make a copy of the string first. Then m, the initial result will be 0. So you say why we still have character, which means why the length of the copy of the string is not 0. So why we still have character inside the string, do get the first character and update the result with the previous result times 256 plus the ASCII code of the first character. Then the temporary string, you update it by removing the first character because you already treated the first character. Do you understand what this is doing? So for example, if I give you the string ABC, this will return what? So you give me a string and it will return an integer. So we can use this to encrypt with the public cryptography. It will return what? So it will return, look at the first thing that we do. M starting 0. We take the first character, which is A. Then the ASCII code of A. So it will be the ASCII code of A plus 0 times 256. So the first time it will be the ASCII code of A, which is 61, no? Let me put it in hexadecimal. 65, sorry. It's 41 in hexadecimal. So it will be 41. The second time that I pass, I already processed the A, so I have the remaining of the string. I take the first character in the remaining of the string, it's a B. So what do I do? The previous result, I multiply it by 256, and I add the ASCII code of the B. Then what do we do? What is left is a C. So the previous result, I multiply it by 256, then I add the ASCII code of a C. So what will be the result at the end? So look at, it will be the ASCII code of A times 256 to the square, plus the ASCII code of B times 256, plus the ASCII code of C. So let me write it again. It will be the ASCII code of A times 256 to the square, plus the ASCII code of B times 256 to the power of 1, plus the ASCII code of C. So if I give you this string, A, B, C, D, it will be what? The ASCII code of A times 256 to the cube, plus the ASCII code of B times 256 to the square, plus the ASCII code of C times 256 1, plus the ASCII code of D. It will be that. Do you agree? So for example, that will be this integer. Okay. So they ask us to do a function that will encode. We are not encrypting for now. We are just encoding. Put it in from a string to an integer. Let's do a new file. Let's call it exercise 11. Let me create a file. Let me give me write. On this file, the user can execute it. Okay, now let's edit this file. Exercise 11. So user bin Python 3. Okay, so they ask us to define a function to encode and call the function encode. And they say after try the function. So encode, receive a string, no? So the input is a string. Input is a string. And it returns an integer. So let me call it result, for example. Result starting 0, as we can see here. Then I will say while the length of the input, or I can just say why the input is not the empty string. What should I do? I take the first character. So I do result is equal the previous result multiplied by 256 plus the ASCII code of the first character. So the ASCII code is ORG. And the first character, how do I get the first character? Input sub 0. Then I need to update input and remove the first character. How do I do that? So I need all the characters starting in 1 up to the end. Isn't it? All the characters starting in 1 up to the end. That's it. And I return the result. Okay, let's see if this works. So let me execute it with Python 3-interactive. So it's code encode. Let's put encode of A. What will be encode of A? 65, isn't it? Which is the ASCII code of A. Good. What will be encode of empty? 0. Good. What will be encode of AB? So 65 times 256 plus 66, which is the ASCII code of A times 256 plus the ASCII code of B. So let's do it. It will be 65 times 256 plus 66. So it should be this number. So let's see. 16,706, correct. We already have this. Let's see it. So look at this integer here. 1, 2, 3, 1, 2, 3, 1, 2, 3. So 1,094,861,636. Okay, it's work, no? As you can see. So I did encode. Let's see what they ask. Write a function in Python called decode that does the reverse operation. Okay, that is a function that receives an integer, which should be the result of encoding a string and return the corresponding string. So I want an inverse function, which means if I pass this function, this integer, you have to give me this string. If I pass this integer, you have to give me this string. If I pass 0, it have to give me the empty string. Okay. We are going to call this function decode. Def decode. So the input will be an integer. And the output, let me call it result, will be a string. So we start with the empty string. So what should we do? While the integer that we have is not 0, we have to keep going. So why not 0? What are we going to do? We are going to take the last character. How can I get the last character? The last byte. The last byte have the last character. I don't know if you realize, for example, let's see that we have this ABCD. So this ABCD gives me this integer, and this integer is not more than for 1, for 2, for 3, for 4. You see, in hexadecimal, it's this one. So if I want the D is here. If I want the C is here. If I want the B, it is here. And if I want the A, is here. So it's difficult to get the A from the beginning, but it's easy to get the D, the last character. How do I get the last character? How do I get this 4-4? This 4-4 in hexadecimal, no? Which is 68. How do I get this 4-4? For 1, for 2, for 3, for 4. How do I get this 4-4? I can just divide by 256. If I divide by 256, I will get this 4-4. Of course, it's going to show me 65, 66, 67, 68. I do the modulus. Here it is. And this 68 is 4-4 in hexadecimal. So how do I get this 4-3? First, I divide by 256, and the result modulus 256. It will give me this 4-3, and 4-3 is 67. How do I get this 4-2, which is the second character? I divide 2 times by 256, and then take the modulus. So it will give me 66, which is the ASCII code of B. How do I get the first one? I divide one more time by 256. So A is 65. Here it is. So it's what we are going to implement in the code. So what can I say? How do I update result? Result equal. So I need the last character. So the last character is input modulus 256. Yes, that will be an integer. Then I need to convert it in a character, CHR. Now it's a character. So what should I do? I say this character concatenated with the previous result. Look at the first time I'm going to get the D. So the second time, the D will be here. And here I will get the C. So it will be C concatenated with D. The third time I'm going to get the B. The B will be here. And here I will have CD. The last time I'm going to get the A will be here. And the result will be BCD. So it's the way that I have to concatenate them. Okay, and how do I update result, which is an integer? I divide it by 256. Eventually it will be 0. When it's 0, I can return. Sorry, how do I update input? Input is an integer. I will return the result at the end. Okay, so this should be the inverse function. Let's verify it. We have two functions, encode and decode. So let me call Python, and let's try, for example, decode of, let's copy I can do it, for example, with this integer. When you don't specify the base, it's base 10, A, B, C, D. Or I can do it saying that, oh, I'm going to give you the integer in hexadecimal. Okay, did work. If I put, for example, let's see, if I put 41, 42, 41, 41, 20, 41, what will be the result? So A, B, A, space A. A, space A. Of course, if I take this integer, if I say encode of B, A, space A, it's going to give it to me in decimal. If I want it in hexadecimal, I can put hex of that. You show me the string. I can also put, if I want, it's like as a string. If I want it as an integer, I can say, yeah, it will be a string at the end. Integer base 16. Integer x give me the value in hexadecimal. Okay, so we have done both functions. Let's continue. So we have to do the function encode and decode. Validate your function with some example. We did that. Bob used the public key. They give us a public key. Alice wants to send the message hello to Bob. Help her to encrypt the message so that only Bob can decrypt it. Okay. So we have E and we have N. We have the public key, so we can encrypt. So we want to send help. So what will be the step that I have to follow to send help? First, I need to convert help as an integer. For that, I'm going to use what? Encode of help. I need to send this integer. This integer is the plain text. So what should I do to find the ciphertext? It's always the same thing, no? You do the plain text to the power of the public exponent. Who is the public exponent? 65,537. 65,537. Modulus n, which is the modulus. Modulus, this big number. I'm going to type it. I'm just going to copy it. Modulus this. So this is what she have to send. She have to send on the network this integer. Okay, do you agree? So let me do it maybe easier. I'm going to put E is 65,537 and the modulus is big number. The plain text, what you want to send is this number. So the ciphertext will be what? The ciphertext will be the plain text to the power of the public exponent modulus the modulus. If I ask, show me the ciphertext, it is there. Okay, I have not invent anything. Okay, so she have to send that. So Alice wants to send the message hello to Bob. Help her to encrypt the message so that only Bob can decrypt it. So she has to send that. Okay. Trudy intercept an encrypted message between Alice and Bob. And this is the ciphertext that she got. So this message was sent by Alice to Bob. Trudy has very high computing power and could decrypt the message. What was the original message? So they want you to compute the original message. So they give you can use the power operator of Python. If you use the power operator of Python, decrypting will last for a long time. You may want to define a function called power mode that will receive three parameters, x, y, and z, and compute x to the y modulo z. We already have this function in Python, which is called power, P-O-W. Look at, they give you a hint. They give you this. So you have all the information. We could compute this. So they give you the private exponent. So D, the private exponent is this one. We copy it. Okay. So what should we do now? To know what is in this message. We take it and we decrypt it. So this is a ciphertext. C is equal to this. What should I write here to get the plain text? To the power of D modulus n. So of course, you're going to do this number to the power of this number. It's going to take a long time. Maybe even hours, days, or years. So instead of doing that, they say, why don't you use the power function of Python? So let's do the power function of Python. Power C D C to the power of D modulus n. So this is the plain text. So what is the message that Alice sent to Bob? Remember, this is an integer. We have to go from an integer to a string. So we have to use decode. We did this function decode, where you give me an integer, I go back to the string. So decode of this crypto. She sent crypto, as you can see. No? This is the message that Alice sent to Bob. Of course, very easy to see, for example, that the last character is a O. What should we do? We take the plain text. We do modulus 256. This is the ASCII code of the O. 79. Let's see. O 79. Then, for example, if I want the T, what should I do? Divided by 256, modulus 256. Give me 84. 84 is a T. So crypto, we find the O, we just find the T. If I want the P, $80, this will be the P. 80 is a P. Okay, so yeah, CD chain crypto. Okay. Now, this we could find we could find it. So let me see. Let's verify that first. It is the inverse of 65,537. How do I show that this number is the inverse of 65,537 modulus this number? How do I verify that? What should I type here? E times D. So they give me the D. Let me copy it here. Modulus, oh, it's modulus phi, no? That have to be 1. We don't have the phi, we need the phi. Yeah, we don't have the phi. What we have is the modulus, so we cannot verify it. If I put n, it will not be 1. Yeah, it's not be 1. We don't have the phi, we need the phi to verify it. So there is no way to verify it unless we factorize this. Now, if we factorize this, let's factorize it. So, factors of this big number. So this is P and this is Q. So let me go back here. I'm going to say the pair PQ is equal to what I just copied. Since I make only one copy, look at what I do. So if I ask for P, if I ask for Q, okay, I have P and Q. So now, what should I verify is that what? This modulus P minus 1 times Q minus 1 should be 1. So this, when I hit enter, should be 1, and it is. So I can say that this number and this number are inverse to each other. Modulus phi. Modulus this number. Okay, because phi is P minus 1 times Q minus 1. Okay, any question about it? Okay, so let's do exercise 6. You are required to calculate the modulo operation given below. First, find a pattern to compute 7 to the n, modulus 15, and then answer the question. So as you can see, it's always 7 to something modulus 15, no? Always. So let's try to find a pattern and to answer this question quickly. So 7 to the 0 will be what? Will be what? Don't tell me that you don't know what is 7 to the 0. 7 to the 0 is what? It's 1 modulus 15. 7 to the 1 is what? Is 7, no? Modulus 15. 7 squared will be 49. And 49, 45, 6, 7, 8, 9 is 4, isn't it? 4 modulus 15, no? Because 49 is 45 plus 4. 45, I will suppress it because it's 3 times 15. Okay, 49 is 3 times 15, which is 45, plus 4. So when I'm modulus 15, any multiple of 15 can appear or disappear. So it's 4 modulus 15, no? Okay, 7 to the power of 3. Let's do 7 to the power of 3. What will be 7 to the power of 3? Modulus 15. So 7 to the power of 3 is 7 to the power of 2 times 7. So I can just say it's the same thing as 4 times 7. 4 times 7 is 28. And 28 is what? 15 plus 13, isn't it? 15 plus 13. So the 15 can disappear. It's just 13. And 13 is what? Is negative 1. Modulus 15. So between the 13 and the negative 1, I prefer the negative 1 because the negative 1 is smaller and easier to multiply. 7 square. What can I do with 7 square? 7 to the power of 4. I can do negative 1 times 7. It will be negative 7, or it will be also 8, no? Mod 15. Let's keep going. 7 to the 5. So 7 to the 5 is 7 to the 3 times 7 to the 2. So it will be negative 1 times 4, which is negative 4. Which is also 11. So you use negative 4 or you use 11 as you want. Modulus 15. Okay. 7 to the 6. So I can use this negative 4 times 7. Okay? So negative 4 times 7 will be, or I can use 7 to the 6. I can use 7 to the 4 times 7 to the 2. 7 to the 4 is 8. 8 times 7 to the 2 is 4. 8 times 4, 32. 32 modulus 15 is 2. So I'm 2 here, modulus 15. Okay. For now, we have not. Let's see, 7 to the 7. What can we do? Is 7 to the 6 times 7. So 2 times 7, which is 14. And 14 is negative 1. Bingo! Negative 1, negative 1. Modulus 15. So I find something. Can you relate this one with this one? Which means that now if I do 7 to the 8, it will be what? It will be 8. 7 to the 9 will be 11. 7 to the 10 will be 2. 7 to the 11 will come back to negative 1. Do you see that? It have to go in cycle. So 7 to the 20 will be what? According to that. 7 to the 20. So it will be, I need to, here we have a period 1, 2, 3, 4. We have a period of 4. So I need to write it 4 times something. 20 is, so I need to write 2. So 2 plus 4 times something. 2 plus 4 times 4 plus 2. So let's say, let me do something easier. What can we say about 7 to the 3 plus 4n? It will be what? It will be -1, isn't it? Look at, for example, if n is equal to 0, it's 7 to the 3. If n is equal to 1, it's 7 to the 7. What can I say of 7 of 4 plus 4n? It will be what? It will be -1. I can write it like 15. Let me put 15 here to make it clear, and we can verify it with a calculator. So this one will be 8. Okay, it will be this one. So for example, if n is equal to 0, it will give me 7 to the 4. 7 to the 4 is 8. If n is equal to 1, it will give me 7 to the 8. 7 to the 8 will be also 8. So it will be 8 modulus 15. 7 to the 5 plus 4n. 5 plus 4n will be what? 11 modulus 15. 7, the last one that we need to do. Is this the last one? Yeah, no. I need to do another one, no? 3, 4, 5, 6. Okay, plus 4n will be what? $11 will be 2 modulus 15. I am done or I'm not done? It will be 7. After 2, I have -1. Oh, it cannot be 15. How can I write 15 here? 3 plus 4n, -1 is 14. This one is 14, sorry. Of course, we are modulus 15, no? So it's 14. Okay. So I think here we can just write 4n. Here we can just write 4n plus 1, because 5 is 4 plus 1. So we can just write 4n plus 1. 4n plus 1. And here 4n plus 2, because 6 is 4 plus 2. So here we can just write 4n plus 2. Let's see. 4n plus 2. So when they ask 7 to the 20, so 20 is what? 20 is 4 times 5. So I should find 8, isn't it? 20 is 4 times 5, so I should find 8. Let's see what the calculator say. 7 to the 20 modulus 15. 7 to the 20 should be 1. Let me see, 174. No, so this formula, no, so I could not make this change that I say. So let me go back. Sorry for that. They were correct. So that was correct. So let's say 7 to the 20 is equal to 7 to the 4 plus 16. 4 times 4. Oh, but there is no 1 here. $13. Oh, 13 is not -1. We have a mistake here. 13 is -2. That's why it was not working. So we have this error and we spread this error all over and nobody told me anything. So let's see. 7 to the 0 is 1. 7 to the 1 is 7. 7 squared is 4, which is 45. Plus 4, which is 49, yeah. 7 to the 3 is 7 times 4, 28. And 28 is 15 plus 13. And 13 is -2. Because I can do 13 minus 15, which is -2. So from there on, everything was wrong. That's why it didn't work. So, okay, let's remove all this and compute them again. 7 to the 4 will be -2, or 7 to the 4 will be 4 times 4, which is 16. So it will be 1. Oh, it's even easier. It will be 1. We already find 1 again. We already make the cycle. So we came back to 1. So look, this was wrong. And the cycle is even earlier. It's from here. We have a cycle already here. So now I think we can write everything. Let me remove all this. Or what will be 7 to the 5? It will be 7 again, no? Because we have a cycle, we come back to 1. So we are going to do 1, 7, 4, 13. 1, 7, 4, 13. So 4, 13. So what do we have? 7 to the 4n will be congruent to 1. 7 to the 4n plus 1 will be congruent to 7. 7 to the 4n plus 2 will be congruent to 4. 7 to the 4n plus 3 will be congruent to 13. And that's it. So with this result, we can find that 7 to the 20, which is 7 to the 4 times 5, will be congruent to 1. This is what Python was saying. 7 to the 20 congruent to 1. Okay. Now, 7 to the 55. What will be the result of 7 to the 55? So 7 to the 55. 55 is 4 times what? 4 times calculator, 55 divided by 4. 4 times 13 plus 3, no? Is it correct? Let's say plus 3. Let's see. 55 modulus 4 is plus 3, correct. So since it's plus 3, which one I'm going to use? This one. So it will be 13. So 7 to the 55 modulus 15 must be 13. So let's do it. 7 to the 55. 13, correct. What is the next one? 7 to the 100. So they ask you 7 to the 100. And look, we don't have to compute 7 to the 100. And we have the result. So 7 to the 100 is the same as 7, 4 times 25. So we are here, it will be 1. So 7 to the 100 should be 1. So 7 to the 100 is 1. And look, if you lose your time to compute that, it's a big number, as you can see. We don't have to compute this big number. And we know that it's 1. 7 to the, for example, 244. What will be 7 to the 244 modulus 15? 7 to the 244 is the same thing as 7. So 244 divided by 4 is 61. Oh, this is 4 times 61, so it will be 1. 4 times 61, it will be just 1. So 7 to the 254 to the 244, sorry. 7 to the 244 is a big number. Modulus in will be 1. Modulus 15 will be 1. If I do this one, it will be what? The result. So it's not 244, it's 244 plus 1. So it will be, according to our, it will be this one, it will be 7. So it will do 1, 7, 4, 30, 1, 7, 4, 30. So 1, 7, 4, 13. Again, 1, and 249, we have 250. 4, 13. Again, 1, you see, 1, 7, 4, 13. We do have, as the exercise says, we do have a pattern to compute 7 to the n. Okay? Okay, it's time. So we are going to stop here. Do you have any question? No? When is the homework due? Homework number 2? The one undergraduate? Is due tonight? Okay, is due tonight? Okay, I hope you have make progress on that, no? Okay, so the homework is due tonight. Please don't forget to upload your solution. Okay? Okay, I see you next week.